Okay, so I'm happy to be here in Paris, and I'm happy to speak at this inaugural conference for Claire. So the topic, I will talk about moduli of K3 surfaces. And let me say that I hadn't really, somehow, it was not my plan to start working on the moduli of K3 surfaces, but it became required for certain integrals that we were studying. So I wanted to just say a few words about that. So if we look at, say we have some K3 surface S, then one can look at curves in S, and there's a moduli space of maps to S, say some curve class beta. And this moduli space, there's a theory of some integration, this Gromov-Witten theory, over this space. This is a long story that's maybe 20 years old by now. And you could try to calculate these integrals. And so this story starts with Yao-Zaslow formulas, and then there's many more, KKV. And there's a theory here. It's about 20 years by now. And in the middle of this 20 years, there was about 10 years where there was no progress. And the reason for this was that what was missing in those 10 years was this idea that you shouldn't think about this K3 surface as static. You should let it vary in moduli. And this is a topic of a different lecture about why letting this K3 surface vary in moduli and understanding its Noether-Lefschetz theory actually helps you solve these integrals for a static K3. It's a strange idea, but it's actually what moved to the final stage in this theory. And by now, so there are still open questions here. It's not everything is proven, but the structure is all understood. And it is the case that, for example, if you have a particular integral in this theory you want to compute, and you lock me and some of my friends and some computers in the room, we can calculate it. There might be some part of that calculation which is conjecture, but we know how to do all the numbers there. But this picture of, so I mean, somehow the idea here is this K3, these kind of problems for the K3, they're exactly solvable. And this picture of this Gromov-Witten theory of the K3 is going to be behind this talk, and at the end it'll come to the fore of the talk. But somehow, so this is some past. So I will talk about some general things, some older, some newer. The newer results are all work with Qizhen Yin. All right, so let M to L be the moduli space of quasi-polarized K3 surfaces. So by this moduli space parameterizes pairs. We have a K3 surface S and a quasi-polarization H. So this should be non-singular projective K3, and this H is this quasi-polarization. So it has pairing, K3 pairing 2L, there's 2L. So this notation conflicts almost completely with Gabi's. So yeah, so I'll help you, don't worry. At a certain point. Yeah, that's right. But you see, this has a bar and this has a G. Okay, we'll have a small discussion about this. This has a bar and it has a G. This has no bar and it has a 2L. But as I said, I can help Gabi and write K3 here. So the difference here is that we're going to almost always consider problems for all genus and all degrees at once. So the L will remind you that this is K3 because no one would ever call a genus 2L. Right? But this is a small part. Actually, part of this talk is mixing the two moduli spaces in your head. So it's not such a bad thing to have the same letter. It helps you psychologically mix them. Okay, so let's start mixing them. So this is the moduli space of quasi-polarized K3 surfaces. And so we can write that here, M to L. And over this is the universal K3 surface. Yes. And if we're in the land of curves, there's the moduli space, the Deligne-Mumford compactification of the moduli space of curves. And over this is the universal curve. And so one thing is immediately should be noted is this space is compact. This space is not. This is 19-dimensional. And it's not compact. But it's not very far from compact, actually. That if you want to compactify it, you just have to add some points and some curves. So this Satake compactification, you add very little. It's just some points and curves. So from our perspective, of course, it'd be wonderful to have a great compactification of this. And there's many. I mean, this is a topic of long research. But we're not going to discuss this now, and as far as I'm concerned, this is rather close to compact, and we don't have to put in lots and lots of stuff just to capture this little compactness we're missing. Okay, so this has a boundary structure. The boundary structure you can write as some disjoint union of some boundary moduli spaces that map in. And these are indexed by graphs, more or less the topological type of the boundary. If you fix this topological type of the curve, you get some graph, and it goes into the boundary here. So how to think about the boundary of this space is, this is maybe more, well, anyway. But somehow the parallel for this perspective here is the boundary here is also a disjoint union of some discrete data. The discrete data is a lattice. This lattice contains the quasi-polarization. That's the 2L. This is why in some I index it by 2L, because that's a lattice of rank 1 that's given by one number. So, and then we have some moduli space of lattice polarized K3 surfaces, and they map into here. So this is where the Picard group jumps, and jumps by all possible lattices. So in some sense, this is not exactly, I mean, the parallels here are only supposed to be somehow suggestive. In the sense that this is a finite number of boundary pieces. Here, there's really lots, in some sense dense, but nevertheless. Okay, and so here, there's a study of some tautological classes. And how does a tautological class come? Well, with respect to this map, the universal curve, there's a canonical sheaf. In fact, it's called the canonical sheaf of this morphism. And if I want to make a class here, I can make a kappa class. And this kappa class comes by taking the first term class of this fellow, raising it to some power, and then pushing it down. So this gives me a kappa class. So you can index this. I'm not going to put the index here because the index is on that side. So this gives me a class here. This is not the only way to make classes. You can also do this kappa construction on every single boundary and push it forward. So that's the idea here. So now what happens on the K3 side? Well, the analog of this is the tangent bundle. I mean, we could have used the cotangent bundle, but somehow traditional now use a tangent bundle. This morphism has a relative tangent bundle. And this tangent bundle gives us classes C1, C2. Now we don't worry too much about C1 because the K3 surfaces have trivial canonical bundle, which does not mean that this class is trivial. It means it's pulled back from the base, and there's a discussion about that. But anyway, we don't think about this now. It's not necessary. But there's something else, of course, is that these are polarized. So there's also the polarization. So what did I call it? H. Sorry, the font here is actually somehow important. So this is polarization. And now this is also a little confusing because, they're polarized, but that does not give me a line bundle on the universal surface. It gives me a line bundle up to twist. Because so this is H is only up to twist. This is somehow an inconvenience here. And I will fix this later. I mean, there's ways to fix this. There's some actually very nice ways to fix this which are relevant to how I will think about this problem. But anyway, so we have on this universal surface, we have this line bundle up to this twist issue. The twist means up to some line bundle from the base. And we also have this C2. So in some sense, we have a richer language of kappa classes where we take the push forward of some number of this H and then some number of the second Chern class. Okay? So that gives me some tautological classes here, but then we can also play this game for every lattice here. And we can push them forward, exactly as we did here. So if we look at this this construction of the kappa on the lattice, it's just the same on this lattice polarized K3. It's just the same, except we have more choices of these L's, more choices of line bundles, because we have the whole lattice polarizations. We have more than one. You have all of them. So this means if I want to start writing the kappa classes on this lattice, well, I can pick a basis of this lattice and have some number for every element of the basis. So if it has basis B, A, B, and then there's the, A, L, and then B. So this kappa classes, these give you the powers of this line, the line bundles, and then B is still the second Chern class. All right? Yeah, so the Hodge bundle so if I look at this, I erased it, but if I look at this is the pullback, I think, of minus the Hodge bundle. This is a very good question, and it does appear. It appears because actually this Hodge bundle is a line bundle here, and it's a theorem proved in several different ways. You can see that line bundle is actually a linear combination of the push forwards of the Lefschetz divisors. So I'm putting it in without telling you, but it's there. Yeah. This is why I don't put it. I mean, you could put it here like this, but then you're giving yourself more work. Okay, so then we have on the moduli of curve side, tautological ring. So this is low or what? Is this too low for you, Janos? Okay. On the tautological ring, you have there's some tautological ring here, and then on this side, there's also a tautological ring of all of these classes. All right, so I've defined everything in Chow. So this is in Chow. This is a good question. So maybe everything with Q. So you could look at the ring generated by all of these things. So that's a lot of things. All right. Okay, so how to study this? So here it looks like really lots of stuff. The chalk. So how to study it? Well, the experience on the moduli of curve side is you can look at so now maybe I look at just the open part, the smooth curves. You can look at some powers of the universal sheaf, and there's various games one can play about sheaves here, points, Brill-Noether theory, and you can use this, so maybe I can say the geometry here. So Karl Faber's original approach used more or less some kind of classical theory of curves, Brill-Noether theory. Geometry of points leads to relations among the tautological classes. This is again some kind of discussion, but so it's natural to think a little bit what we want to do here. So you could say that for these K3, moduli of K3 surfaces, well, what is the analog of points on a curve? Well, you could just take the fiber product of S, or the universal curve, but that's not such a great thing because if you want to associate elements of the fiber product to subschemes, it's not so great because of, so the natural thing here is the Hilbert scheme of points. So if I use this, this is S. S, that's pi, and so I use this, I write the Hilbert scheme, the relative Hilbert scheme of points. So this gives me some map here. And one can try to use somehow this philosophy that here we had points, we made relations, here we have points, and we have some kind of ideals, and you can try to make relations, and this is not without success. You will make some relations here. But you can see that there's a problem a little bit with this, from this point of view, is that if you use the Hilbert scheme of points just by itself, you're not going to pick up these Noether-Lefschetz loci because these points don't see the curves breaking. So this isn't so good in the sense that you won't see the boundary here. So, but that's okay. You can use something fancier than the Hilbert scheme. You can use a relative quote scheme. So I write what the simplest quote scheme that's useful. I take 2 copies of the structure sheaf of this relative structure sheaf, and I look at the moduli space. This quote scheme is a moduli space of some quotients Q. So it parameterizes these quotients. And now when you define this relative quote scheme, you have to define some classes for this, the Chern classes of this quotient. And now you have a choice. So you could pick, for example, so this Q, you can pick it to have, say, some first support. Its fundamental class is H, our polarization. And then there's also the Euler characteristic of Q, some number. So this is a module. This is a quote scheme. This is a relative quote scheme over this moduli space. It's something fancier than here, but actually, maybe I don't talk more about the moduli of curves. But it's very natural from that perspective also to consider this relative quote scheme. What's sad about it, in some sense, is that it's a complicated space. In particular, it could be non-reduced and singular. You don't have those problems over here. So, but before I address that, it's certainly going to, this kind of thing is going to see our node-left structure, because we have these 2 sections, and if on some node-left locus H breaks up is L1 plus L2, we can somehow distribute those L1 and L2 to the two factors here. So the geometry of this quote scheme, unlike the Hilbert scheme, does see this node-left structure. That's the good part. The bad part is that it's a complicated space, possibly non-reduced and singular, and it's going to be a little bit hard to use. But that's solved by the fact that this space is virtually smooth. This is somehow the crucial point. Otherwise, you can't calculate anything. And what do I mean by that? Is to say that this space has a virtual fundamental class. This relative quote scheme, it has a relative obstruction theory and a virtual fundamental class. So you can use that class to make the relations. Why does it have that? Well, if I look at this quote scheme as I write it as some subbundle, so a subsheaf, if I look at the deformation theory of this, there's the x0 of a q and x1 of a q. So these are the deformations, relative deformations, so in the fiber, obstructions. And then one worries about this x2 of a q. But this, by Serre duality, this group is dual to x0 of qa. This is the K3 case. And this is a Hom from Q to A. If I ever had a Hom from Q to A, then I could continue that Hom to here, and this would give me a torsion sheaf that's a subsheaf of a locally free. And this cannot happen. So this is 0. In fact, this argument didn't use the fact it was K3 very much, because if the surface weren't K3, then there'd be a tensor product with some canonical bundle, but the argument would still hold, meaning that if I replace this moduli of K3 surfaces with some moduli of surfaces, any moduli of surfaces, there's this relative quote scheme. What was important was this is a torsion sheaf. That means it's supported on curves and points. That this construction gives you some virtual class on some relative quote scheme over any moduli of surfaces. And in some sense, this kind of study should also be somehow the first step into understanding how to write classes and relations among moduli spaces of other moduli spaces of surfaces. And they're all different. They have different character, even from this perspective, because the virtual dimensions depend a lot on what surfaces they are. Okay, so now one has this idea that you can use the virtual class on this relative quote scheme, and you can make relations. I don't say exactly how you make relations out of this, but you can use localization. There's various ideas. But the important thing, every idea goes through at some point pairing with this virtual fundamental class. It allows you to calculate. It's something non-trivial, allows you to calculate. And this geometry picks up both the kappa classes and the Snow-Lefschetz loci. So you can write down relations. And we did this. This was a paper last summer with Alina, Marian, and Dragos. This was, I think, 2015, I guess. We did it, and you get relations among those classes that I wrote, but the relations are complicated. But nevertheless, you can calculate them on computer, and the outcome is that leads to certain predictions. So I'll explain. There are actually two outcomes. So the first outcome is that, well, you can calculate these, but the coefficients were hard to compute. And the reason was that what happens is the coefficient, the numerical coefficients of the relations, will involve integrals over the Hilbert schemes of points of K, the simplest case, even more. The Hilbert scheme of n points in a K3 surface and various tautological things, and you'll need to calculate this number. This is some number, and in order to calculate the relation, you need to calculate that number. And these numbers are hard. In some sense, we know how to calculate. There's various approaches to calculating integrals over the Hilbert scheme of points. It's Nakajima calculus, and you can calculate them, but it's not to prove anything, you'd need to be able to have some kind of formulas for this, and we were not able to do it. In fact, something else happened, which was kind of fun, was that there are integrals that came up here that we could calculate using these methods to calculate. So, for example, the simplest one is so these are integrals that just come there in this calculus. If I look at this Segre class, I should look at the formula. So this is the standard notation. So this polarization, I get a rank n bundle on the Hilbert scheme, and I can look at the Segre class. This is an example of integral. And as I said, we don't make this stuff up. When you go do this, it'll just come there. And you need to calculate it. And it turns out that this integral was considered by Manfred Lane. And he had a conjecture, actually more general conjecture. But in particular, he had a conjecture for this. And this was quite a long time ago, 1999, in his Inventiones paper. There's a conjecture he wrote a conjecture for this integral. It's an incredibly simple conjecture. There's 2 to the n, L minus 2n plus 2, choose n. Okay, that's a pretty simple formula. So yeah, we could prove this formula. So we couldn't calculate the general coefficient, but there's the various, these integrals just come in naturally, and by playing the games there, we could calculate this, so we could actually prove this. This gave actually the first proof of this, actually the only proof we know of this formula. So this was one of the outcomes of that paper. So this is kind of unexpected outcome in the sense that we were hoping to use the formulas to prove something with the relations, but in fact, the outcome was proving this formula. And there's a certain subject that opens here about how to use these relations in this geometry to write down exact formulas for various calculations of the Hilbert scheme more general. Okay, but we're not going in that direction. I just wanted to explain one of the things that comes out. So what somehow comes out that's more relevant to the path of this lecture is that it became clear from looking at these equations that this entire tautological ring, the one that I defined, actually is much simpler than it looks. There's a certain subring, which we call this Noether-Lefschetz subring in here. And this is the subring generated, actually it's additively generated by the classes of all of the boundary. So every boundary you throw this in, this gives you an additive subgroup at every level. And in fact, that turns out to be closed under multiplication if you do the things correctly. And what became a very natural conjecture from this, because we made a lot of relations, but we couldn't prove it, was, so this is conjecture, is that this is actually equality. And also for other lattices, I state it here in the easiest case, which is saying that in the beginning of this talk, I was mostly wasting your time with all these tautological classes. That there was some kind of big zoo that I explained, but in fact, that the subring given by just the class, the fundamental class of the node Lefschetz loci to generate everything. So that, I said this was a conjecture made. Basically, you could see so many relations, it was a natural thing to conjecture. Okay. So so what's known, so one of the statements is in this R1. Yeah, so this was conjecture from 2015. Before that, I think about 10 years before that, Devesh and I had conjectured what happens in code dimension 1, which is somehow a stronger conjecture, which says that this node of Lefschetz 1 in this language is equal to all of the Picard group. So this is you can say some piece of this. This conjecture, so this was, I think, more than 10 years ago with Devesh, and this was proven by Bergeron, Lee, Milson, Merglin. Okay, but that's not the whole thing. Now, this particular conjecture, so we have a proof of this in Chow. This was just this summer, 2016, but that's with Qi Zhang. So this is true. This is with Qi Zhang, Yin. And also in the summer was announced by Bergeron and Lee a proof of a weaker statement about this being true in cohomology in most cases. So that's the situation. But in fact, this is true in Chow in all cases. So I wanted to explain a little bit about how we prove this. Yes. Why? How could it not? No, but no. Yeah, you just apply the cycle map. Yeah. Okay, so I wanted to say a little bit about how that goes, but before I do that, I want to explain something else. Which has to come back, which has to do with this compactness. So if I look at this tautological ring, M2L, we would like to have some numerical theory. If this were compact, we could get some numerical theory by some integration on the whole space, but it fails to be compact. So then how can this be addressed? So I don't want to repeat the parallel story for moduli space of curves, but there are methods there, and it has to do with some kind of vanishing. So this thing here is 19 dimensions. Its complex dimension is 19. So, so the conjecture, and this is more or less from the spring, and this is based on kind of optimism. There's actually not really such great evidence for this conjecture. Anyway, I hope it's true. That if I look at 17, this should be one-dimensional. Conjecture, maybe this is more like wild hope. And then these fellows afterwards should be 0. Okay, so if this were true, then there would be a full numerical theory also here, which you could ask for pairings into this 17. So now I tell you what little evidence for this is. In the summer, Dan Peterson, he proved that these two vanishings hold in cohomology. I don't know if you view this as strong evidence or not. The vanishing of the last one is obvious in cohomology. So about this, the only thing we know is that there exists, it's a theorem that this is not 0. It's not 0, and that's because it has a non-trivial element, which is this class lambda that Claire asked about, the 17. This is not 0. This is easy to see because this guy's fellow is ample, and we have 17-dimensional compact varieties because of the fact I said the space is almost compact. This was first observed by Gerhard van der Heer and Katsura.
There's no issue with quasi-polarized?
What?
I mean, this Pandharipande isn't it for quasi-polarized?
Yeah, I'm always on quasi-polarized.
Okay, there's no polarized.
Yeah, I never said polarized. I always said quasi. Yeah, you've got to, this whole theory, you've got to do quasi-polarized, otherwise you're mostly wasting your time, I think. Okay, so there's one other little piece of evidence that I'm almost afraid to utter, but I think that there's this true, I think that this Q, if I look in cohomology, so you have to concentrate here, 34. In the case of 2, I think this is true, although this contradicts the literature. Okay. I don't know if you view that as evidence or not. But right? So this is a very small amount of evidence for this. Another question, so I think these are kind of interesting questions, especially these bottom ones. There's probably some way to address them, but you need to know more about K3 surfaces than I do. In fact, I know relatively little about K3 surfaces. But this is like this one, this R18 in the total. This is something interesting about lattices. All right, something else you might ask is NL star generated by divisors? This is kind of almost natural to expect, and almost everyone who, if I mention this problem to them the very first time, they say, well, of course it's generated by divisors, because every time you pick up, the lattice grows, you pick up one more, and that's the intersection. So it's a very natural thing to think. That argument is false, because when you pick up that intersection, there could be other intersections. But actually, this is false. So proposition, and this is something I discussed with Dragos in the spring. Actually, Devesh and I, years ago, had basically addressed this question, and we decided it was false, but I don't think we ever had a proof. With Dragos, well, there's kind of a proof also. I'll tell you the proof. So no, this thing is not generated by divisors. The proof is that I look at M2. I should say that this subject, there's one calculation that's been done somehow completely, which is the very first one, M2, and that's by Francis Kirwan and Lee. And this is by studying every term in this, you can learn a lot of things. And I encourage people who know a lot about K3 surfaces to calculate. So I hope someone does this. I would be very happy. Calculate all of the singular Betti numbers of M4. Okay, there's a lot of them, 38. Calculate them. This would help a lot. So in the case of M2, it was pretty hard work. They wrote several papers. First there's the intersection cohomology, and then there's calculation of the cohomology. This is pretty complicated, even in this case. It starts by the GI, like in Karen's talk, you start by the GIT model, and you blow it up, and you use these formulas, you use this language of how to calculate the cohomology of the quotient from the Puig quotient, and it's a kind of long, hard calculation. This is, of course, harder. But anyway, if you look at this calculation, I don't have the numbers here with me, but the Picard is rank 2, and if it's going to be generated by divisors, it's very hard with rank 2. So the Betti numbers here grow too quickly to be generated by divisors. But then you need another theorem to show that the things, even though they've grown too quickly, that they're still in this ring, and that follows from work by this group here. So there's actually rigorous proof it's not generated by divisors by just studying this calculation that was done 20 years ago. Okay, so, but I really would hope so. I think it's degree 4 or something like that. It's very close to the top. Yeah. Okay, so now I want to explain a little bit about how Qi Zheng and I proved this. And that goes back to the beginning of this talk, which is about Gromov-Witten theory. So yeah, So this subject is full of lots of very nice questions, I think. And I think that some of them are probably not impossible. Like this one, I think, is definitely possible. It requires a certain commitment. Okay, so in some sense we start at the beginning again. And what happened to my... Okay, we start at the beginning, and now we have to address something that I let slide, which is how to normalize these. When we work with these tautological classes, it's a little bit unpleasant. I mean, the idea of this and this whole calculus is you write down symbols, they have precise meaning, so you don't want to have meaning up to normalization and all that. So there's a very nice way to do this. So if I look at, say, this moduli space, and it has this universal surface, and now instead of looking at the quote schemes, I do something else, which I look at the moduli space of stable maps. So there is here a relative moduli space, and it's for every genus, but let's start with genus 0. And it has for every number of points, but let's start with 1 point. So it's pi relative, and in the polarization class. We could pick also multiples as polarization class, or if it's a lattice, we could put an element of lattice class. All right. So there's this is a moduli space. This is a moduli space of rational curves with a point. But this again has a virtual class, virtual fundamental class. And all of these theories is to reduce. I mean, there's a discussion about what kind of perfect construction theory and how to make it non-trivial, and that's very important, but I'm not going to discuss it here. But this has this virtual fundamental cycle, and what's the dimension of it? This is this virtual. So we usually call this reduced. What is the dimension? Well, one part of the dimension is the base dimension. That's 19. Then there's a dimension. This is the cycle dimension, not the codimension. Then there's a dimension of how many genus 0 curves are on the K3 surface, the virtual dimension. That's 0. Well, that was pretty easy. And then there's the point. This is 20, okay? So this cycle is actual 20-dimensional cycle. And there's a proper map, the evaluation map at the point. We have one map point and we evaluate it. So if we push forward this, this gives me a beautiful class, which now I try to change the font. So we start with a straight H, and now I have a calligraphic H. Okay? Because this thing is 19, this one's 21, and this is a 20. And this is really a cycle class. We've defined it perfectly. And there's no normalization. We actually have one class. And what is this class? This class is basically the class defined by adding up all the rational curves in there. Right? But it's defined, it's defined in this Gromov-Witten way. Okay.
So it's a multiple.
It's a multiple, right? So you can divide. So I think we normalize it. And this is this Gromov-Witten number. So we can normalize it to 1 as a class. So we will, but if you use this idea, and you use it all for everything, for all the kappas and everything, that gives you this canonical normalization. You don't never have to talk about up to twists and everything ever again. It's this, all right? Okay. And I should say that it's this idea that if you take a line bundle on a K3 surface and you should add up all of the rational curves there and gives you an actual physical divisor. This was first told to me sometime in the 90s by Sean Keel. And he wanted to use this idea to compactify the moduli space of K3 surfaces. And anyway, this is what we're doing actually. But this is really natural here. You'll see that this is actually fundamental to what we do here. Okay, so now we try to do the same thing that I tried last summer with Dragos and Alina, which was that we look for relations, but now we don't look for relations in using, there's many ways to look for relations using this virtual geometry, but one can say it like this. We look at here mg, maybe you have some n or not, let's say pi h, So there is this modular space of stable maps to the fibers, and this modular space also has a virtual fundamental class. And whatever games were played before, we can play here. And so we have these two sides. One was the code scheme side and the stable map side. And after 15 years of studying this Gromov-Witten DT correspondence, we know, although some things are not proven, we know that these methods are essentially equivalent. That the relations that are going to come from the quote scheme side, this is the kind of sheaf side, and what comes from here, from the map side, they're going to be equivalent. That's for sure, because this is some kind of manifestation of this Gromov-Witten-Donaldson-Thomas correspondence. So one knows this from the beginning, and you have a choice on how to do it. So in 2015, the choice was to use the quote scheme, which has some advantages. Roughly speaking, there's this Nakajima calculus that tells you how to do all the calculations. There's no obstructions to doing the calculations. The problem is that they're hard. This side, we don't know how to do all the calculations. But it turns out we know how to do some of the calculations. And the philosophy is that if you can do the sheaf side, that's like the summation of all the genera. That's why it's nice. It does the genus summation for you. But instead, we can just take here, the genus has something that's a little bit, basically now one views that when you're doing these integrals, you should always be doing on the sheaf side because you get this infinite summation of the genus. And we only live a finite amount of time, so we should do this infinite summation. But what the genus gives you is it gives you a way to, if you're like a child, you can start slowly with genus 1, and then you can go to genus 2 and 3. It gives you this kind of filtration and difficulty, which is absent on the sheaf side. The sheaf side gives you the entire answer in one blow, but it's hard. So here, what's the thing that's actually lucky here is that conjecture about the Lefschetz equaling the entire tautological ring turns out to be implied by just geometry in genus 0 and 1. So I don't know whether this is but this is lucky. So this is actually why we're able to succeed, because we use very low genera, and so the complexity is much less. We can't execute this side in all genus, and we just can't do it. But here, we can do it in genus 0 and 1. And how does this stuff work is you look at M, 2L, S. Well, let's say we can put here. Now, I just used the fiber product. So we have these maps, and this maps to M, G, and bar. Okay, this is a perfect diagram for Gabi. So here I can help him. K3, there. All right? So we have the modular space of curves. These are the relative maps. They map to the modular space of curves. They also map to the universal K3 and down here. And so there's this export process where if you take a relation, we really know relations here. We've been studying this for 30 years. I personally have been studying for 20 years, but people have been studying for 30 years. And so we know really well what's going on here. Basically, we know all the answers. There are some questions we haven't proven, but we know all the answers. So the idea is to take relations here. We start with some relation in the modular space of curves. We can pull it back. You get a relation here. This is how this works, has to do with the splitting axiom in Gromov-Witten theory, the foundations of Gromov-Witten theory. It tells you how to make this step. This has to do with axioms of GW. You don't have to think. So you take something here. Here you have to think, because it's extremely non-trivial to find these relations, but we're totally on top of it. Here you don't have to think, axioms of GW. Then you push forward this relation, you push down here, and you get a relation here. So that's this export process. You start with these relations, you move it around, you get a relation here. Now this last step about how to go from here to here, we don't know how to do in all genera, and I'll give you some very interesting problems about that. But we know how to do this in genus 0 and 1 in the cases we need, and actually the relations that start here, the only ones you need to prove that the Lefschetz statement is the WDV relation and Getzler's relation. So this is in M04 bar, and this is in M14 bar. And these relations are proved in the cycle level, so there's some calculations that are involved, so let's see. Okay, so I want to at least write some things that are connected to Claire's work and the work with Beauville. And there's many ways that now I could go, but let me try to do that since it seems appropriate here. I should make this comment that it's obvious from this perspective how the Noether-Lefschetz divisors occur, by the way, is that when I look at, say, M04 bar, the relation looks like this. And if I distribute the curved class so it breaks, then this will happen on another Lefschetz locus. Or if I have further graphs, so roughly speaking, these things here are described by some graphs, and they have some nodes, and you distribute the beta, the curved class on it. When that curved class breaks, then you get something that's Noether-Lefschetz here. So they occur also naturally there. So maybe I try to write down a formula. Okay. So Getzler's relation is a relation in M14 bar. And I'll explain what you get by taking Getzler's relation, moving it up, and all the way down. You get a very nice relation. So this is a theorem in my paper with Kijang. So we're looking in, this is a relation in 5 cycles on 4 copies of the universal K3 surface. Why 4 copies? Because Getzler's relation has 4 points. All right. And this relation is H1. Okay, this is the first term in this relation. What does this mean? Well, this is telling you this is this class H on the first point. That's the divisor class on the first. I told you how to take H to make a curly H of the divisor class. That's the one on the first point here. And these are diagonals. So this is codimension 5 total. And then there's 5 other terms, which comes from all the symmetric relation, so all the combinatorial possibilities of this. You can diagram this by saying this is 1, 2, that's the diagonal. This is 3, 4, that's a diagonal. And I put the H on this piece. It doesn't matter which one. And how many things are there like this? Well, I have to pick the set of 2, 2. There's 3 of them, and I have to pick where the H goes. So there's 6 of them. There's 6 of those terms. So that's the first one. And then now the second. So this is actually a really pretty fun calculus to work in. We had a lot of fun in the summer calculating these things. So now there's this. This is the diagonal where all 3 points are together, and that's the H on the first point. And how many terms are there? They're like this. This one has its 3 brothers, 3 others. So it comes from the picture 2, 3, 4, and then the H is over there. Oh. And that comes the minus sign, and then there's this H. 1, right? And this comes also with 3 brothers. This is the diagram 1, 2, 3, and the H lives here. Okay? And the claim is this is equal, so plus dot, dot, dot is equal to 0 in A5 S4. And what is this dot, dot, dot? These are classes. So tautological classes, just explicit ones I've said. Explicit tautological classes supported over proper Noether-Lefschetz loci, meaning something smaller in the base. So they're in this term, in the language of the beginning of this talk, they're the boundary terms. All right? And they're explicit. You know, we calculate. They come from Getzler's relation has about 10 terms, and each one produces these. Some of them live in the beginning, some of them live in the general part, and other people live in the boundary. But they're just there. You just calculate. You can calculate. There's an explicit form. I mean, they have to be. They live here. So, are they all codimension 1? No, I think there's codimension. No. So this is a good point. He's saying that. They don't, some of them are naturally supported on codimension 2 in the base, because you can have, and in fact some are in codimension 3 in the base, I think. So you can have up to 3 breaks in there. Yes, exactly. Yeah, we're coming to that. As I said, so I wanted to make some contact with your work. Is that so? There's a paper by Voisin, and Voisin, which is probably around 2000, which is about the diagonal decomposition for K3, and this is also about is it 2000? Is that right? No? 2004. Okay, fine. It's about the diagonal decomposition, and you get exactly their relation if you do the following thing. So this is about moduli. So we can intersect this with a fixed moduli point. But you do something else. So first of all, that's about 3 points, and we have 4 points here. So actually you take this relation, let's just call this relation rel. You multiply it by this curly h, say at the 4th point, and then you push forward, forgetting the 4th point. So this is the push forward to the first 3 points. This gives you a relation in. I could calculate the number in a second. I don't know. We can look in a second. That's 3. I'm getting it's 2, 3. 4. Perfect, yeah, 4. So you take this relation I said, that gets the relation, you hit it with this one more, you push it down, you get a nice relation here. That relation, again, has boundary terms, everything. But then if you want to make contact with the Voisin, this Beauville-Voisin calculation, you fix the moduli point in K3, and then you just precisely get there. Then these terms, this is a nice exercise, you precisely get their decomposition of this diagonal decomposition in Chow. That thing is really important. Yeah. What are they? Oh, everything looks about the same. The boundary terms you have, so they all come from Getzer's relation. So if I look at the general term in Getzer's relation, it's codimension 2, okay? So the general term in Getzer's relation will have two, a kind of graph in Getzer's relation is like this. We have a genus 1, 0, 0. This will be a graph, it's a codimension 2 and M1, 4. So here are the 4 points, it's codimension 2. And then if I see how this contributes to the boundary, it contributes in several ways, but the deepest way is I can spread a class. I can spread my curve class and break it into 3 times. This corresponds in general to a lattice of rank 3. And then this, when I write this diagram, then the rules of Gromov-Witten theory tell me what I should put here. And all of these are going to survive in your relation too. So there's going to be the Lefschetz terms with Picard rank 3, there's one with Picard rank 2 and Picard 1. What's very interesting also is that the principal term of this relation has no numbers in it. No numbers. They're all 1. But when you look at the boundary terms, then very interesting numbers come up. For example, the number,
So if I look at the open subset of the number space where the polarization cannot be written as a sum of effective or 2 effective divisor classes, over that open subset, the Beauville-Voisin relation holds with no correction. Is that what you're saying?
No, that's not. I mean, that's almost what I'm saying. There's something else I said, is that there's also this lambda class that comes up. And I also expressed that in the boundary. And this may or may not occur. So, I mean, I can make a precise statement, but these things will certainly die in that locus. But in this calculus, there are some other people that come in. Oh yeah, I was trying to say something interesting here. So these coefficients are all 1, which is kind of remarkable. But when you look at the boundary, then all sorts of beautiful things are growing in the boundary. So of course there'll be this Gromov-Witten number. But this will mostly go. The most interesting thing is this guy. This guy will come in. There's a genus 1 Gromov-Witten number. They'll just come in the boundary coefficients. And there is some question about what is their meaning of it, in the sense that a relation like this up to boundary is only defined well up to other boundaries. So it's not clear exactly what the meaning of that is. But these numbers, when you write it out, these Gromov-Witten numbers come. And it's certainly good that we know we can control them all. Okay, so I want to make 2 remarks. So one is that if you take this relation, this is a relation that lives upstairs. It lives on the fourth fiber product of this universal K3. That's just a single relation. But since it lives upstairs, I can multiply it with lots of stuff and push it down. It gives me infinitely many relations on the moduli of K3 surfaces. And these relations are enough. Well, this one with the WDVB friends are enough to prove that theorem. And that's some kind of playing with equations. In our paper, there's 10 pages where we use the linear algebra of these relations. But it's easy in the sense that very often in this kind of linear algebra, there might be complicated matrices to invert and all that. None of this happens. It's kind of easy. The second thing I wanted to say before I finish is that, I said it's very lucky that that theorem can be proven with just genus 0 and 1 because we can handle them for various special reasons. But this export procedure about moving relations in the modular space of curves, the modular space of K3 surfaces, it's valid. It should be valid in all higher genus, and I want to explain at least a little bit of why we can't do it. And this is also related to, well, that's like a fixed K3 surface. And we're tired of moving it all for the whole lecture. It's like a fixed K3 surface. And there is maybe we take n copies of it. Then there's a genus G. This is the modular space of stable maps in some class H. And it has the evaluation map. So the n-fold evaluation map. And here is the virtual class, the reduced virtual class. And we can consider the image, the cycle, this algebraic cycle, which is the full evaluation of this. And where does it live? Well, it lives in some algebraic cycle. It's some kind of really canonical algebraic cycle. So somewhere you can calculate the dimension, of course, in n copies of the K3 surface. And one thing, so conjecture one, well, this conjecture I don't know how to prove, and it's embarrassing. I mean, I wish I knew how to prove it. And maybe it's not even so hard, but is that this cycle lives in this Beauville-Voisin ring. So I remind you what that means here. That means we look at this, we look at all of the cycles that are generated by the Picard group on this side. It probably might only need this element of the Picard group. This is what I would guess. And the diagonals, and the Chern class C2. I mean, anyway, it's in their papers. But there is a particular ring here that people who study this like very much. And I would very much like to prove this thing is in it. It's almost certainly true. And one of the things, basically what's stopping us from writing that export procedure in all genus is that we need to know this is here, but we need to know, of course, more than that. We need to know the formula for it here. Once we know that, then this kind of export procedure can really be put to work. Everything, I mean, everything. Oh, which do I know? Yeah, not so many. So genus 0 and some, it's possible we know it for all. And I have to think about it, but certainly for the ones we need for this. So this is genus 0 with some small number of n and maybe 4. I don't know, I have to go look. But roughly speaking, genus 0 and genus 1 for small number of n. Genus 0, maybe we can do it for everything. But genus 1, I know for a fact we don't know it for 4 or 3 maybe. I don't know, I have to check. It's actually embarrassingly small, the number of times we know how to prove this. But that is enough to prove that theorem. Just barely enough. But this is, I think, a very simple question, and it really cuts to the heart of the relationship between, I mean, the fact that I don't know how to prove this means that it really, there's some kind of really missing, some aspect of this is missing from, theory's missing. Okay, I think that's all.